In this video, we're going to look at different examples that are useful and really important for exponentials and logarithms. So first thing we want to talk about is radioactive decay. So we did see an example of this in a previous section. We were talking about radioactive isotopes, and what we're going to look at is something really important with radioactive decay, and it's the concept of half-life. So with half-life, it's the idea of how long it takes some radioactive isotope to reduce to half of the substance it started with. Okay, that's the idea behind half-life. So real quick, mathematically, what we'd be working with is this basic equation. So this is similar, by the way. It's the other version of the equation where instead of writing B, you write 1 plus R. And R could possibly be negative if you're talking about a decrease, which, by the way, we would in these problems since we're talking about decay. Or it could be positive if you're talking about increasing. Okay. But for us, we will be talking about decay. They are, however, using the more easy to work with equation, H of T equals A, B to the T. And to find the half-life, we would be taking half of what it originally started with. And in these equations, the original amount is A. So we'd be taking half of A. So taking half of A and then figuring out what B and T would need to be. Because in this equation, when I look at this, I could cancel the A, and basically I'm trying to figure out when B to the T is going to equal 1/2, because then it'd take half of the original amount. So that's the kind of approach we'll use when we're looking at half-lives, is kind of taking this idea of taking half of the original amount. We might do some different values, but we'll keep connecting back to half-life as we are working through some examples. Okay, so let's look at this example. Let's suppose bismuth-210 is an isotope that decays about 13% each day. What is its half-life? Okay, so how long is it going to take before it gets to half? That's what we're interested in. So if half-life is based on this principle, 1/2 equals B to the T, and we know that B could also be rewritten as 1 plus R to the T, we know what R is. R is negative 13% since it's decaying by 13%. So this becomes 1 minus 0.13 to the T, or we're basically trying to solve this equation. 1/2 equals 0.87 T. So to solve this equation, I'm going to need to use natural logs. Now, I kind of stupidly did it in the middle of the page, but that's okay. I'm going to take the natural log of each side. I should have enough room. Or a regular log. You don't have to use a natural log. You could use log base 10 if you want, whatever you prefer. But we're going to take the log of both sides so we can bring the T down to the front. And solve for T by dividing by natural log of 0.87. And you grab our calculator and take the natural log of 1/2 divided by the natural log of 0.87, and I get 4.977. Which, if I'm just kind of answering the question, I could say that it takes 5 days. That's the half-life, about 5 days. Or if they want more accurate decimal, 4.977 days. Okay, let's look at another example. Cesium-137 has a half-life of about 30 years. So if you begin with 200 milligrams, in 30 years, you would be left with what? Well, this is just literally taking half of the 200 milligrams. So in 30 years, we'd be left with 100 milligrams. Another 30 years then, we're going to be decreasing by half again. So 50 milligrams. And in 90 years, we'd be left with 25 milligrams. So this example is just to kind of demonstrate how the half-life is working. Every 30 years, we're literally taking half of what we were at that moment. And what you'll notice, though, is that if you keep taking half-lives of something, there might be microscopic amounts still left. It might be too hard for us to trace, but there's going to be like tiny amounts possibly still left. Now, this is really useful when we start becoming interested in carbon dating, but we'll get to that in the next example. Coming back to this cesium-137 and a half-life of 30 years, let's find the annual decay rate. So in 30 years, it's going to get half, but every year, how much is it decaying by? That's what we're interested in. So now they are asking for R. That is what they're asking for. So we're going to use the other version of the equation. 1/2 equals 1 plus R to the T. And we know that in 30 years, that is the time it takes to reach 1/2. So to solve this equation, I actually don't need to use the natural log. I can take the 30th root of both sides, but really I'm not going to take the 30th root. Really what I'm going to do is raise both sides to the 1/30th. That's just easier to put in the calculator. 1/30. Okay, so 1/2 to the 1/30. Now I'm going to leave this in my calculator so that I can refer to this decimal in my calculator to stay as accurate as possible. But I get 0.97716. That equals 1 plus R. Then from this, I'm going to subtract it. I'm going to subtract 1, which is going to give me a negative R, but that's the decay. So minusing 1 gives me negative 0.0228 or 2.28% per year. That's the decay rate annually. It decays and gets rid of about 2% each year. Okay, now here's how it works when we're talking about things like carbon dating. So carbon-14 is one of the longest decay rates. It has a half-life of 5,730 years, which is why we use carbon dating on objects, because often there's still carbon left in the object for us to measure so we could figure out how old the object actually is. All right. So in this example, if a bone fragment is found that contains 20% of its original carbon-14, how old is the bone? Okay, so there's a couple ways of approaching this. In fact, the textbook uses the alternative continuous formula. So instead of working with the formula we've been working with this whole time, which was, I'm trying to remember, f of t equals a b to the t, or the 1 plus r version of b instead, you could technically use the E formula, e to the rt, and they switched to that, kind of just saying, well, it's more common, but I'm not going to do that. And if you want to see how they do it, it's very straightforward. We're going to stick with the formula we've been using just because we've been using it. We're used to this formula. So we're going to use this formula. We're going to use the 1/2 b to the t. But in this case, I am going to use the R version, the 1 plus R version, because if I'm interested in figuring out how old the bone is, it's going to be useful to me to know the decay rate, the annual decay rate of carbon-14. All right. So I'm going to need to find the annual decay rate real quick for carbon-14, and then I will take that and use that information to figure out how old this bone is. Okay, so I need to find the decay rate real quick of R to the 5,730. I'm going to do just what I did above. I'm going to raise both sides to the 1/5,730. We're basically taking the 5,730th root of both sides. And we're going to get 0.99988. Actually, I could solve for R, oops, but I just realized what they just basically gave us was B in the equation. I think we can just work with that. You know what? We're just going to work with that. So rather than work with 1 plus r, maybe I'll just change this back to b. Sorry. Made a command decision there. Call it b instead. I could find r, by the way, if I subtract 1. R is going to be very small. 0.0002 or 12, blah, 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 blah. It's going to be very small, but that's okay. I found b. I don't know why I didn't write it in red, though. That's so weird. Let's switch that. 99988 equals b. Okay, so I found b now. So here's my equation that I'm working with. F of t equals a times 0.99988 to the t. Now we are working with 20% of the original amount. So 20% of the original amount, which is a. I'm going to basically use the trick I used earlier. Cancel the a's on both sides. And I'm left with 20% equals 0.99988t. Wow, those nines are so sad looking. And then to solve this, I'm going to take the natural log of both sides so that I can bring the t down. And divide both sides by that natural log. Now, I kept this in my calculator, didn't round the number. And I would try to keep your decimals in the calculator so you get the most accurate answer possible. If you put this rounded number in there, you're going to get a little bit different answer than me. The final answer probably wouldn't matter, but it does kind of bother students when you get such a different answer. So I'm going to divide both sides by the natural log of 0.99988 on both sides. And this on the left is what I'm going to plug into the calculator. Okay, so natural log of 0.2 divided by the natural log of that decimal, which in my calculator is the previous answer. So I just put that in as the previous answer, and I'm getting 13,304. Now, if you use the rounded number, I think it comes out to like 13,311 or 411. I mean, it's actually quite a bit off. Here, I'll plug it in and I can tell you how off it is. 99988. Okay. Oh, I put in the wrong thing. I used 0.5 instead of 0.2. Couldn't understand why my answer was very, very off. Okay, 13,411. There we go. So it's like a long time off, like 100 years off. Okay. I think the final answer, they'd probably have you round. So it's about 13,000 years old, right? Or 13,300 years old or something like that. Yeah, they'd probably have you round your final answer, but it would be very far off if they wanted you to round to the nearest 100. So try to use as much of the decimals possible. If you don't know how to pull an answer in your calculator from the previous thing you just entered, just write the whole decimal out and put that whole decimal in, and it'll give you the most accurate answer you can give. All right. So it's about 13,300 years old.